Welcome everyone. My name is John Ruiz. I work for Johnson Controls. I work in a part of Johnson Controls which builds batteries. What I want to speak to you today is a piece of technology that actually spans between buildings and batteries. It's called stationary energy storage. So let's dive right into this. So if you look at an electric bill for any type of a commercial or industrial consumer, it's built out of three parts. The first part is an energy charge, where your bill is based upon the amount of energy that's consumed. So if you use more energy, you get charged more. It's a kilowatt hour type of charge. There's typically two types of rates that are applied to this type of system. The first would be a standard charge rate where it's fixed throughout time. So it's 20 cents per kilowatt hour, for example, for as much energy as consumed. Second way that it's done is what's called time variable rates. And time variable rates, the rates change based upon the time of day. So if it's difficult for utilities to maintain electricity, rates go up. If it becomes easier for them to maintain electricity, rates go down. And in a commercial building, you would typically see that during the day where rates would be high, and then in the evening where rates would be low. The second part of a energy bill is what's called a fuel surcharge. Fuel surcharges are a way for utilities to buffer themselves from commodity changes. So if they're buying coal or they're buying oil, these are commodities that change on the open market and can vary in price. So if there's a certain threshold that utility has where if the price of the commodity goes above that threshold, they add an adjustment to your electric bill. If it goes below a certain threshold, they add a negative adjustment to your electric bill. But in any case, it depends on how much you consume is the amount of adjustment that you get. And if energy prices are stable, like they have been for the last couple of years, that adjustment turns out to be zero. The last thing that is part of your electric bill is what's called demand charges. And demand charges are really a way for the electric utility to recoup an investment that they have in providing energy for your buildings for very short time of the day or very short times of the year even. So there's an infrastructure they have to put in place that's required to be paid back, and these demand charges are the way to get that payment back. So for example, if you have a building that's well run and consumes a certain amount of energy, during the hottest days of the year, it may consume twice as much energy, sometimes 3 times as much energy. Well, during those 3, say, hottest days of the year, utility still has to have generation, it still has to have transmission, it still has to have distribution in place so that it can provide enough energy for you to run your building. So for 3 days a year, the utility has overbuilt their entire infrastructure in order to satisfy your needs for the hottest days of the year. So the demand charge is what helps the utilities recoup that. So in one analogy, it's if you look at it kind of from a energy flow, they're not charging you for the amount of energy that's flowing through a pipe. They're charging you for the thickness of the pipe. If you get a bigger pipe because you consume more energy, very short periods of time, it costs more than if you have a smaller pipe. So every month your electricity bill is energy you consume, it's some type of fuel surcharge, and then it's a demand charge based upon how peaky your energy is, how much you consume at any particular time of the day. The interesting thing is if you look at the energy market, the prices for energy have been stable or sometimes even declining. So utilities are trying to move the market, and regulators are trying to move the market from being a price certain market to a price responsive market. So instead of charging you 10 cents per kilowatt hour, they're going to charge you 3 cents per kilowatt hour during the evening and 10 cents per kilowatt hour during the day, so that they want their customers to react on that and to turn things off during the day and maybe turn them on at night if they can shift their loads. And customers have been pretty effective at doing that. So the utility is starting to increase the number of programs that they have that allow you to do that type of energy manipulation. Customers have been responding to that, which has been keeping the energy prices down. But as you keep those energy prices down, what happens is you get a level load across the day, but then the peaks, the intermittent things that happen during the day tend to stand out even more because you have a smaller base you're starting from And then you have these peaks that kind of pop up during the day. So demand charges have been going up. So because of the fact that we have had stable energy, which has reduced the consumption within a building, and because we're starting to get more and more renewables put on behind buildings, when those renewables go intermittent, when the wind stops blowing, when light, sun goes behind the cloud, you get a reduction in generation, which is causing peaks in the output of the consumption of your facility. A well-run building can have 30 to 70% of their electric bill each month based on demand charges. So it's not how much you're consuming, it's how peaky your load is that's important in these things. So how do you get rid of the peakiness? How would you want to stabilize your energy consumption? There's actually an easy way to do this. It's what's called peak shifting. You take energy that you use during the day and you somehow store it at night and then shift it over to where those peaks occur. It's a pretty simple concept, and there's multiple ways to do that. So if you look at a typical load profile of a building, in the evening there's less energy consumed. People are gone, the lights are off, the computers are shut down. During the day, as people come in and start generating energy, as your lights get turned on, as your computers get started, your consumption goes up. So if you can store that energy at night, hold on to it, and then during the day when those peaks occur, fill in those peaks. To the utility, it looks like you're consuming less energy, which means you're charged less for your demand charges, which stabilizes your energy costs. So how would you go about doing peak shaving? There's a number of ways you can do it, and they're all cooperatively good. So you can do all of these or none of these or any combination of these, and you can reduce your energy consumption. The first way is the easiest way. Use the stuff you already have. So if you have a building that has a building control system in it, you can program that building control system to reduce the peakiness of your loads. You can turn things off during the day and start them up in the evening. If you can move some of the energy, say through cooling through, say, mass, having your building retain some of your cooling the building more in the evening and using that cooling up during the day. Or you can move loads or schedule loads when they're not being occupied, again reducing your consumption during the peak heavy times of the day. You can use thermal storage, in this case an ice storage system, to create ice in the evening, use it during the day to go and displace cooling load. And again, that will reduce your peak and level out your consumption. You can use generators. For example, a combined heat and power system would be very good at reducing peaks, assuming that you can use the excess heat, the waste heat that's generated from that system. Generators themselves as a technology, though, have some inefficiencies around them. They're combustion engines, they have very low efficiency, and they have some environmental issues with them. So it's typically you don't buy a generator just to do peak shaving. And then the last one, electrical energy storage, is a direct way that you can control the electric energy that's provided to a system. Because it connects directly to the grid and consumes electricity and provides electricity, you get higher efficiency, so it brings more power out of the system and puts it into the system. Very low maintenance because it's a battery system. And the system itself works in any weather condition, whether it's hot or cold, and it can be monitored and controlled by any type of a building control system. So if we just look at a short example here of how electrical energy system might work. So again, we look at the typical profile of a building where in the evening you're not consuming as much power, but during the day you're consuming more power. Your battery would recharge itself in the evening and level out that load, and then would displace its energy during the day when you're at a higher peak rate. So you save money at the high peak rate because, again, variable pricing means that you're paying more for energy at this time than you are for this time. And because the efficiency is high, you're not really losing out on that savings. And then you are trimming off your demand charges because you're reducing your peak down. So I have an example here, which is an example of a very large building. It's actually a campus example in this case. In this particular case, we have a 500 kilowatt system with a 500 kilowatt hour system. So it's 500 kilowatts of power that you can use for 1 hour in duration. And if you can think about it a little bit, this is like a small shipping container full of batteries. So it's not the type of thing that you're going to wheel on the back of a cart. It's the type of thing that gets put in place and put on a concrete pad outside of a building. But it also works for smaller buildings too. This happens to be an example for a larger one. And we're at the point now where with this type of system, the system itself goes and reduces the peaks for you, but it also provides you another benefit that the other types of peak shaving systems don't. It provides you what's called energy security. So if indeed you were to lose your power, this particular battery kind of system could provide backup power for you. In this case, it could provide, say, 1 hour of backup if you had a 500 kilowatt load. But it gives you the security to know that if your power were to go out for some short period of time, you could use the battery to go and provide that power that you need until the utility can come back and provide you power. So in this example, we have a very large campus that's providing about a half a megawatt of power, and we're using that to shave the peaks. This particular building is placed in one of the areas that provides incentives for energy storage. And right now, the industry is at the point where incentives make this work. So you have an annual savings of about $130,000 and a state incentive of $400,000. And this gives you about a 3-year payback in this kind of a system. So we're talking about $750,000 worth of batteries that are sitting in your backyard. A lot of money, 3-year payback for a very large campus, not a bad proposition. But again, it's based upon state incentives. The projected cost of the batteries for these type of things, they really have been going down because they're used in multiple places. They've been going down because they're used in cell phones. They're used in computers. All of the batteries you see in cell phones and computers are the type of batteries you would use in these type of systems. And they're projected that within 5 years that you'll get this simple payback without any type of incentives. So we're really on the early end of this particular technology being cost effective, but it appears that it's going to be in these type of applications. Energy storage is just one piece of a much bigger puzzle. Energy storage itself doesn't really save you energy. It moves energy, it consumes energy when energy is cheaper and moves it into time when energy is more expensive. So it's not saving you any energy. But it's a tool that you can use in order to get to a greener building. In the same way that you would look at your kind of life cycle of a building, you should include energy storage in that. You want to reduce, you want to generate, you want to store, and then you want to analyze. And you want to continue that loop till you get to a completely green building. Thank you for listening to this. I hope you learned something out of it. I hope you enjoy the rest of Greenbuild. If you have any questions, I'd be happy to answer them.